I just noticed.
Thank you. Well, too bad. How much did we go? Did we go like 20 minutes almost? All right, sorry. Okay, that's why you got to attend live. So just unfortunate, because I am human and I make mistakes, which are mostly unforgivable. Like this is a pretty bad mistake, especially when it's snowing right now, but I'm sorry. All right, then, as we said, we must look at our body B, right? So when you look at our body B, right? So what forces do we have for our body B?
Yeah, weight and normal force again.
Weight and normal force again. So you'll have, oops, let's see. Let's say, you know what? I should have said that this guy was M subscript A, M subscript A, like that, right? Obviously. Right, so here you have M subscript B, G, like that, right? And then you have the normal force, which is, equal and opposite to the one we had, but obviously we're smart and we knew this, right? And then we know that this angle here is going to be, because it's with the horizontal, right? So this angle here is going to be 20 degrees. Right? And then we draw the kinetic diagram. So now things are getting interesting, right? So now you'll have these two accelerations. You can write it off as an unknown, right? So you can write off, all right, so it's like this is moving down, this is moving down. So there'll be some acceleration of B like that, between where A is and where B is. But that does not help us, right? We don't know where the direction of B is. And then you'll get additional unknowns in terms of where the angles and things are. But we've done this, right? We know that the acceleration of B is equal to the acceleration of B relative to A and the acceleration of A. And for both of these, we know the direction, right? B relative to A is going to be sliding along here, and A, the acceleration of A, is sliding down on this incline over here. So instead of drawing that guy, we can do is say that we've got the acceleration of our body B relative to A, and you've got that sliding motion down, right? So you've got, it's going to look something like that for your acceleration of B relative to A. And we know the directions of these two. That's why it makes it easy, right? So what I mean by that is that if I look at this terrible drawing, give me a second, guys, let me just fix it. Like that, right? Draw this angle. So we know that this angle is equal to 30 degrees. And we know that that angle is equal to 20 degrees, right? And now we can define a new coordinate system, which will make our lives easy. So let's say that we're looking at Y and X like that, right? So we're looking at stuff relative to the block. So if we write out our expression, well, since we'd already used Y and X over here, let's just not confuse things. Let's say Y prime and X prime like that, right? Then we look at sum of forces in this Y prime direction is going to equal MB time whatever acceleration you get, you'll have to take the components of the accelerations here, but you'll be smart. You'll only have a component of AA because you defined our coordinate system in a smart way, right? So if you write those equations out, so in the positive y prime direction, you've got NAB, right? And in the negative direction, you'll have the component of MBG. So MBG, and will it be cosine? Yep, cosine of 20 degrees, right? And that is equal to this component of MBAA, but now it's in the negative y prime direction. Signs always carry forward as well. So it'll be is it clear that this is an equal to sign over here, guys? I just wrote it vertically, right? This is equal to over here because I'm writing my equation like that because I don't have space over here. So it's minus MBAA times sine of 50 degrees. Good. This is your second expression. You know what? Just so that you guys are not confused, let me write the equation out again. It was basically NAB minus MBG sine of 20 degrees is equal to minus MBAA sine 50 degrees. Right?
Wasn't it cosine 20 degrees?
Yes, sorry, thank you. Cosine of 20 degrees. All right, so now you have two expressions for two unknowns, NAB and AA. Right, let's not get into the arithmetic of it because we're running out of time. Solve 1 and 2 for AA and NAB. And Mathematica for these kind of things is muy bueno. It makes things really easy, but we're running out of time. So I'll just give you guys the answer. Basically, you're not so much interested in NAB, right? You're more interested in AA. So the easiest one, if you want to do it by hand, is to just eliminate NAB. Wow, messed that up big time. NAB from equations 1 and 2, right? So if you do that, you'll end up with, and plugging in for everything, you get that AA is equal to G, which is 9.81. All right, times you know what? It's not easy taking shortcuts in life. So let's just write it out. Eliminating NAB, you get, and plugging in for your, what are we plugging in for? Yeah, masses and everything. So you get,
so these two equations are being solved together.
basically two equations for two unknowns, right? NAB and AA, but we're more interested in acceleration. That's what I said. Plug these into Mathematica or your calculator and get your answers directly, or you just solve it mathematically, right? So plugging in all of the values, we see that 22 times AA minus half G divided by cosine of 40 degrees is equal to 10 times G times cosine 20 degrees minus AA sine 50. That's it. Nothing there. So here you can solve your AA. Turns out to be equal to 9.81. And units, be always careful. We're skipping that step over here, but you guys be careful, please. Plus cosine 20 cosine 40 divided by 2.2 plus cosine 40 times sine 50, and this comes out to be equal to 6.4061 meters per second squared. Right? And now, to find out the acceleration of B, right, we also need to find out the acceleration of B relative to A. So for that, we just look at our Newton's second law in the x prime direction. So you'll have your Newton's second law in the x prime direction. That's equal to mb, and whatever the acceleration of your body B is in the x prime direction, right? It's just going to have two components. So for this one, let's see, for the forces in the x prime direction, you'll only have a component of the weight, right? Because the normal force is in the y prime direction. So you have mbg, I believe it's going to be sine of 20 degrees, right? Then you have your two accelerations. So you'll have a b relative to a, which is going to be positive, and then you'll have the component of a in the negative x prime direction, right? So that'll be a cosine of 50, right? So this is going to be mb times ab relative to a minus a times cosine of 50 degrees, all right? And here you have one equation for one unknown because we already know what AA is, right? So this is the way that we're doing it, and this is how it's traditionally done. How I typically do the problems is I just set up my equations and I just find the number of equations with the number of unknowns and just solve for everything in Mathematica. Save a lot of time by doing this algebra, right? And we'll see when we go on later on in the class, it's going to become more and more complicated, but this I thought was like a happy medium for you guys as we're transitioning over, right? So if we solve over here, you see that the acceleration of B relative to A is equal to G sine 20 degrees plus A cosine of 50 degrees. That, so plugging it in, you get 9.81 sine 20 plus 6.4061 cosine 50. This is going to be in meters per second squared. And you guys can check this. Sorry, guys, we're running out of time. So 4730 meters per second squared. Now you can find out the acceleration of B as a vector, which is, it depends on completely upon you guys, whatever you think is easier to do, right? Because we are concerned with the vector expression, right? So acceleration of B is equal to acceleration of B relative to A plus the acceleration of A, like that, right? Or you can solve it using triangles. That's completely upon you guys, right? So if we draw it out, right? So you have the acceleration of A, right? So this is the acceleration of A, which is 6.4061. I won't put the units in here because everything's we know that everything is fine. So this angle here is 30 degrees, right? And then you've got the acceleration of B relative to A. something like that, right? So this acceleration is acceleration of B relative to A, and that's equal to 7.4730 meters per second squared, right? And then we know this angle is 30 degrees, this angle is 20 degrees, right? And then you get this acceleration that we've been waiting for, which is the acceleration of B, right? So acceleration of B is equal to acceleration of A plus the acceleration of B relative to A, like that, right? And let's say that this angle is some unknown angle alpha, right? Now, choices. You can do it in IJ and get your answer like that, totally okay. Or you can use sine rule, cosine rules, and things like that, right? So just to keep things holistic, we use our cosine rule, right? So AB squared is going to equal AA squared plus ABA squared minus 2A, right? So it's just 6.4061 squared plus 7.4730 squared minus 2 times 6.4061 times 7.4730. And this is the angle. So whenever you're looking at the cosine rule, it's the opposite angle, right? So it's going to be cosine of 50 degrees, right? So this is cosine rule. Right? So you solve this expression and you get that your acceleration of B is 5.9447 meters per second squared. And then you also want to find an angle, right? So find this angle alpha by using your sine rule. You can say that 7.4730 divided by sine alpha is equal to 5.9447, which is this guy divided by sine of 50, right? Like that. So you solve that and you get alpha is equal to 74.4 degrees, like that, right? So now you found a magnitude and a direction for your acceleration. So now for the next part of the problem, you're asked to find the velocity of B relative to A, right? So with that, we just have to be concerned with and it starts from rest, right? So for the velocity of B relative to A, right? If you remember your expressions, right? It's V plus whatever your initial position is, which is going to be starts from rest. So let's just say it's your initial velocity is, sorry, it's 0, right? So V is equal to V naught plus acceleration times t, right? You guys remember this? So we can just say that for V of B relative to A, that's just, so this guy is going to equal 0 because it starts from rest, plus the acceleration of B relative to A times the time t, right? So this acceleration is 7.4730 meters per second squared times 0.5 seconds, right? That comes out to be equal to 3.74 meters per second. And we know that the velocity of B relative to A is going to be in that direction, right? So we already know that it's in this 20-degree direction. So write that out and say that is the direction, 20 degrees, like that, right? Again, you can write this out as a vector if you'd like, take your cosine theta, sine theta components and write it out in an IJ format. That's also totally acceptable. All right, before we move on to the next question, which we only have 10 minutes for, well, not even 10 minutes, 5 minutes for. So we'll do the setup for that one. Any questions with this one? No? All right, let's move on. So now we've got a 0.5 kilogram block B, which is on this slot, which is cut out on this arm OA. And this OA is rotating in a vertical plane, and you're told that the rod has a constant angular acceleration of 10 radians per second squared. And you're told that when theta is equal to 45 degrees and the radius, so basically the distance from the point O of this block is 0.8 meters, and the velocity of the block is 0, you're asked to find the force exerted on the block by the arm, right? So basically, what is the force that the block is, that the arm is exerting on the block? And you're also asked to find the relative acceleration of the block of this block with respect to the arm. All right. So let's see. We might go a little bit over time, guys. So sorry about that, right? So when you're looking at the free body diagram of your block and your kinetic diagram, right? So let's see that that is your block, right? So you'll have its weight, which acts downwards. Right? And you'll have the normal force, right? So you'll have the normal force, which is exerted on the block due to this arm OA. So let's say that is the normal force like that, right? And you're told that this angle is equal to theta over here. Right? What kind of components should we use?
Polar.
Polar, right? Because you have r and theta. Hints, right? Proof is in the pudding, right? So you'll have it in the same direction as the arm, right? So that'll be MAR. And then, assuming that theta is increasing, we can say that you'll have an MA theta like that, right? So now for this problem, we're told that theta is equal to 45 degrees, right? We're also told that the radius at the instant at which we're interested in, not the radius, sorry, the distance r of B from O is 0.8 meters, right? And you're told that the angular acceleration is equal to 10 radians per second squared. And you're given the mass of your body is 0.5 kilograms, right? And you know that the weight is just equal to the mass times the gravity, right? So now, when we look at, so the first part is basically we have to find out what this normal force N is, right? So that's the force exerted on the block by the arm, right? So for that, let's do obviously the sum of forces in the theta direction, right? So that's equal to MA theta, right? So for that, you'll have positive N direction, right? So N positive in the theta direction, minus the component of W, which is going to be mg times sine 45, right? Is that right? Yep. Like that. And we know that this A theta is equal to M times R times theta double dot plus 2 R dot times theta dot, right? So here, now the trick is, all right, we're given theta double dot, but what is R dot and theta dot, right? It's given in the problem, right? Because we know that when theta is equal to 45 degrees, the velocity of the block is equal to 0, right? So we know that at this instant, the velocity is 0. And the only way it can be 0 is if all your components are 0, right? So VR, which is R dot, that's equal to 0. And V theta, which is R theta dot, is also equal to 0, right? Because V is completely equal to 0. So what this means is not only is r dot equal to 0, but from this expression over here at this particular instant, theta dot also has to be equal to 0, right? So this whole term here just goes away. Is that clear to everyone? Okay, then you just solve it, right? So n is equal to or m times g sine 45 degree plus r times theta double dot, right? So you get m, which is 0.5, g, which is 9.81, sine of 45 degrees, r, which is 0.8, and theta double dot, which was 11, and that was in radians, right? Radians per second squared, not 11, 10, sorry. So units are all good, right? Always, 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 guys, in your problem, if your angular stuff is given in degrees, make sure you convert that into radians before you do your math, all right? That's just a quick mental note. Like that, right? So we end up with normal force of 7.468 newtons, right? And we know the direction is at 45 degrees, right? So problem solved.
You said always convert to degrees?
Always convert to radians. It's just a good
Radians.
rule of thumb. Always convert your degrees into radians when you're doing when you're looking at angular velocity and angular acceleration.
So when you have sine 45 degrees there?
No, that's fine. So your calculator knows what sine 45 degrees is. But here, for example, if you were told that the angular acceleration, whoops, thanks PowerPoint, is radians per second squared, right? This could have been in degrees per second squared as well, right? In order to use it as r theta dot like that, you have to convert that angular velocity and angular acceleration instead of degrees per second or degrees per second squared, always into radians per second and radians per second squared, because that's the dimensionless, the radians is a dimensionless quality, right? That's the only way that your dimensions are going to make sense. Make sense? All right. Okay, and then for the next part of the problem, you're asked to find the relative acceleration of the block with respect to the arm, which is just going to be what? What's that going to be? In terms of the accelerations for r and theta that you get. It's just going to be the rate of change of the rate of change of r, right? Because it's sliding down over here. And also everything else, theta dot is 0, so that gets taken out of the picture anyways. All right. So Fr is equal to mass times acceleration in your r direction, right? And the only force that you have in the r direction, the normal is in the theta direction, is going to be your mg cosine 45, right? So you have mg cosine of 45 degrees, right? And that is equal to m r double dot minus r theta dot squared. Now, in this problem, life is easy, right? Theta dot is equal to 0. But if this theta dot was not equal to 0 and you were asked to find the movement of B relative to OA, it would still just be this R double dot term, because that's the movement that the mass B is going to have with respect to OA, right? This is kind of an intuitive thing that has to make sense to you, right? Relative to OA, B is just going to be sliding along R, right? So the acceleration of B relative to A will always be R double dot, all right? But here, life is easy, theta dot term is 0, so we just find out what R double dot is, and we don't have to think too much about it. So R double dot is equal to, does the M cancels out? Yep. So we get G cosine of 45 degrees, right? And this turns out to be equal to 9.81 times cosine of 45 degrees. which is equal to 6.937 meters per second squared, right? So AB relative to rod is equal to R double dot. That's going to equal 6.94 meters per second squared. And at that particular instant, we know that it's in this direction here, right? So we know that that's at a 45-degree angle. So we know the direction as well. Good. Questions?
So if it was acceleration from B to A, it would not be, so it would just be R double dot.
That's right, always. And we saw this, look at the problem that we did last week as well. It was the same concept. All right. Okay, thanks guys. I'll post, watch out for the homework. And then for the exam, what we'll do is I will, first of all, apologies for going 5 minutes over. And for the exam, what we'll do is that, you have your big problem set and you'll have the solutions for those as well. For the homeworks, because, it's up to homework 3 and homework 3 is going to get assigned today and it's due next Tuesday. I'll only post the homework solutions next Tuesday. So you'll only have, whatever, Wednesday and then Thursday to look at the homework solutions. I hope that's all right with everyone. I can see Mr. Rushford disagreeing with me. So yeah, that's all right. All right. Thanks, guys.